Hello. So we are going to see how AlphaGo and its successors, AlphaZero and MuZero, actually solve the game of Go. So I suppose that you know already a bit about the game of Go. It's a very ancient game where you have a 19 times 19 grid, two opponents, one plays the white stones, the other the black stones. So at each move, each player puts 8 stones at some position on the board. The goal is to cover the most space, so there are rules that if one white stone is surrounded by 4 black ones, then it dies, take it away, then the territory is claimed by the opponent. So it's a very complex game, because the action space is very huge. You have 19 times 19 possible actions, minus the ones which are already occupied. A lot of possible states, so all possible configurations of the Go ban, so which is the board. It's around 10 to the power of 170 possible states. You have around 250 actions available at each turn. And a game lasts 150 moves. So the total number of possible games is 10 to the power of 761 or something. So that's really gigantic. You can never do a full search of all possible solutions. In comparison, in chess, which is already a hard game, but AI was able to solve it, you have 35 possible actions, and in total that's 10 to the power of 120 possible games, which is still huge, but less huge than with Go. So that's why people were thinking it took some time for AI to solve the game of chess and being better than humans. But here the ratio between the different games is so huge that we will need 20 years at least to solve it, and exponentially increasing computational power. So when DeepMind in 2015 came up with AlphaGo, the first Go AI, it was really a complete surprise for everybody in the field. Nobody thought it was possible to be as good as humans as this game so soon. So first a bit of history, how this kind of two opponents game were solved before. They all rely on the minimax algorithm that you have seen in the course Introduction to AI. So simply you have two opponent games, so the squares, that's you control that player. You have different actions which are possible, and then your opponent is playing, different choices, then you play, then the opponent plays, and so on. So at the end you have a gain, which is what the max player, that's you, is receiving. Your goal is to maximize the gain, to call it as a reward, for example. You may want to get the highest reward when you have just 3 actions, like in this very simple game tree, which is 16. But you will never get 16, because to get it, you will need to make that move. But your opponent plays optimally. That means it will never take that action, so that will allow you to win 16. It will take that action, because you can maximally gain 3. So it's a minimax algorithm, because you try to maximize your gain, but your opponent is trying to minimize it. So it's for zero-sum games. What one player wins is lost by the other. That's most competitive games. And the rewards, so the gains, are not arbitrarily numbers like this. Most of the time it's +1 when you win, -1 when you lose, and 0 when you have a draw, something like that. So your opponent tries to beat you and you try to beat your opponent. So minimax is quite simple, because you traverse the tree backwards, so from the leaves to the first action that you want to make. Of course that's a recursive algorithm, but let's ignore this. So we say that when it's your turn to play, you are going to maximize the gain, so take the action that has the maximum value, and you do that for all the nodes. Then you think, what would my opponent do, trying to minimize my gain? maximize his gain. So here it will pick this action, the 4, here it would pick the 5, and here it would pick the 3. That means when I am in that state, I have the choice between 3 actions. One when I will win 4, the other 5, the other 3. So I'm taking this one. So actually in this game, the best I can expect is 5. So I take this action, my opponent picks this one, and then I pick this one. It's maximization when you play, minimization when your opponent is playing. So that's simple in a sense, but game trees can be very long, so the tree can really become huge. So most of the time you don't go until the end of the game. You say, I will plan a couple of steps ahead. You replace the real game, so you never win a game after just 2 moves, by an estimation of what will be the gain when you are in that situation. It's called a heuristic function. In some sense, that's the value of the state. What's my expected return when I am in the state? What can happen afterwards? So if you have this kind of heuristic function, you can do a depth limited minimax. And so just develop the tree for a couple of moves ahead, replace the value of the leaves with estimations, and then you apply this algorithm. There are even more advanced methods like alpha beta, which consist of not exploring the whole tree, leaving parts which are obviously not a solution. For example, here you have done the first part of the tree. You're trying to evaluate this node. You see here I'm going to get maximally 3 when I'm in that state, because if something better comes up here, my opponent will never take it, so at best 3. And so that doesn't make sense to explore this part of the tree, because if I take that option, I get at least 5. So here, as soon as I see that at best it will be 3, that's smaller than that, then I don't need to explore anything in that direction. So that allows to go a bit faster in that search. So alpha beta is in practice the implementation of this idea of minimax. It's really just expanding the game tree, replacing the value of leaves by a heuristic function, and you explore the whole tree intelligently if possible to just pick the best action, you let your opponent respond, and then you replan. It's like MPC. You expand the tree from that state until another depth and search what is the first action I should do. Then you observe what your opponent is doing, and so on and so on. So you can use alpha beta on simple problems, like the game of tic-tac-toe, because there's not that many possible states, 20,000 or so. So the tree can be totally developed, and you search really the whole game tree for the best solution. And the solution is, if both players play optimally, you can only get a draw. And that was also the idea behind IBM Deep Blue. It was the first AI to beat the world champion Garry Kasparov in '95. Deep Blue was implementing alpha beta with 6 moves ahead. So it planned in the future 6 moves ahead and replaced the value of the leaves with some carefully engineered heuristics. So they got help from chess masters to get a situation and describe it with a number, how good it is. So of course it's very difficult to implement. That means if your queen is there and there is a tower in that region, then it's good, but if it's there, it's bad. So it was really all the intelligence of IBM Deep Blue was in that heuristic, because the algorithm is a kind of brutal search in the game tree. So that worked because they had a good heuristic and the game tree is not that big. In Go, it's not possible because the branching factor, so how many children a node can have, is huge. 200 possible actions on average in each state. So if you start from one state, then you have 250 in the next one. 250 times 250 in the next one, and so on. That's exponential. So even if you plan 6 moves ahead, that means 10 to the power of 15 states in that tree. So even if you are able to evaluate 1 billion nodes per second, that's still 11 days to plan 6 moves ahead and make the first move. And then you do it again for the next move, 11 more days, and so on. So that was the main limit of tree-based solutions, because the game tree in Go explodes very quickly. You have so many actions possible in all states, then you cannot really search in that tree with a horizon which is good enough to replace situations with heuristics.